Today we're going to be taking all the information we've learned on function transformations and graphing functions using those transformation methods. Now we've learned basically you can categorize them all into four categories. First we learned horizontal shift, then we learned horizontal flip slash stretch shrink, then we learned vertical stretch slash flip slash shrink, and finally vertical shift. So what I want to do is show you a kind of a formal slash informal proof as to why this method for graphing transformations will work. Alright, so we're going to start again with our p of x, which is our parent function, and we're going to take that chart and we're going to try to reach an f of x transformed function chart. So if we put all of those things together, it's going to look like this. F of x is going to be a times, so this is your vertical stretch slash shrink slash flip, times our parent function of b of x, so b represents your horizontal shrink or stretch or flip, b of x plus c. Now plus c is your horizontal shift. Remember, if c is negative, it's going to move to the right, and if c is positive, it's going to move to the left. We've already went over that in a previous video. And then finally, all of that plus d is going to be your vertical shift. If it's positive, it moves up, straight forward. If it's negative, it moves down. So suppose x1 represents all of our standard x values. So typically this is what we use, -2, -1, 0, 1, 2. Sometimes we use like 0, 1, 4, 9 for square root function and some other values for trig, but let's just suppose these are our x values. And x2 represents our new transformed x values. So remember, keep in mind what we want to do. We want to find x2 values to plug into f of x that ensure we keep the same p of x values from our standard x1 values. Now again, the reason we want to do that is because we don't want to go off the chart. If we just plug in -2, -1, 0, 1, and 2, it might be so far off the chart. For example, look right here. Even after we plug in 2, it's going to be so far off the chart we don't know what's going to happen with that y value. So we want to keep a standard zoom level, so we want to keep those original p of x values. So that's part of the reason. Another reason is we want to compare it to the original parent function. Okay, so in other words, we want p of x1 to be equal to f of x2. Whatever our original parent y values were when we plug in x1, we want to get those same y values for these x2 values. So the question is, what are these x2 values? So we're going to treat that like an algebra problem. So again, here is what we are given. We're given f of x equals a times p of bx plus c plus d. Now it's important to note, if a is 1, b is 1, c is 0, and d is 0, then there really hasn't been any transformation whatsoever. In other words, f of x would be equal to p of x, but they still have values to them, right? So no matter what, we can find some value for a, b, c, and d. Now we're trying to solve for x2, so we're going to replace x with x2 in both parts of these sides of the equation, totally allowed. And then in our proof, we're assuming that p of x1 equals f of x2. In other words, they have the same y values. So we're going to replace f of x2 with p of x1. So now we have p of x1 is equal to a times p of b times x2 plus c, all plus d. Now realize this is a little bit more advanced than what some of you are used to, and that's totally fine. So you might have to look at this for a little bit to fully grasp what's going on. But next, what I'm going to explain is that we want the inputs for p to be the same. Again, that's going to ensure that we get the same y value back. We get the same y value of our p function back, which is what we want to maintain. Looking at this graph, it'd be like these y values, -8, -1, 0, 1, and 8. We want to keep those. That's what's going on in this proof. So set x1 equal to b times x2 plus c to ensure we get the same p values back. And then we're going to solve for x2 because that's what we want to know. We want to know which x2 values to use. So we're going to subtract c. Right here we can see our horizontal shift. Now again, if c is positive, then it will shift to the left. If c is negative, you'll technically be subtracting a negative c or adding c. It just looks this way in the proof. Okay, so then you get x1 minus c equals b times x2. Next, you're going to divide both sides by b. Now you can see your horizontal stretch slash shrink, and now we've solved for x2. So x2 is going to be equal to x1 minus c over b. In other words, we can plug in the standard x1 values from our p function into the transforms function as long as we do what? we first have to subtract c from them, so that's our horizontal shift, and then divide by b. Now again, if c is already negative, you're going to end up adding it because you're subtracting a negative. So just do the opposite of whatever's going on with c. That will give us the correct x2 values that will ensure that we maintain those original y values for our p function. Now if we go ahead and substitute that back in, if x2 is indeed equal to x1 minus c over b, what's going to happen is our b's are going to cancel, and then our c's are going to cancel in the proof, and we end up with f of x2 is equal to a times p of x1, our original y values, plus d. So final part of the proof is, and this is really straightforward, our new y values, in other words, given that our x2 values are equal to x1 minus c over b, our new y values are just going to be a times our original y values plus d. So all that means is you're going to take your original y values, now that you've changed your x values, x minus c over b, you're going to take those original y values, multiply them by a, and then add d. The resulting equation tells us that to get the correct transform y values, all we need to do is multiply the original y values, p of x1, by a, and then add d. Okay, so to summarize, if we take our standard x1 values, normally -2, -1, 0, 1, 2, subtract c, and now again, if c is positive, you're going to end up subtracting, and if c is negative, you end up adding it because you're subtracting a negative. Anyway, just do the opposite of whatever it is. If it's x minus 2, add 2. If it's x plus 2, subtract. Then we're going to divide by whatever b is. This will give us our correct x2 values. The correct f of x2 values can be found by multiplying the original p of x1 values by a and then adding d. So I'm going to go ahead and do this in one video. This is the easy part now. The easy part is understanding, or just doing the steps, okay? So first of all, whatever c is, if it's plus c, you're going to end up taking your original x values and subtracting c. That will give you the horizontal shift. If it's of the form minus c, then all you have to do is add c to your original x values, and that will give you your horizontal shift. In other words, it'll shift to the right. This is an example of what that would look like graphically. So first of all, we're going to do c. Okay. Next, we're going to go to b, which is a horizontal stretch, shrink, flip. Remember, if b is less than 0, it will flip. If the absolute value of b is less than 1, meaning if it's a fraction, it will stretch. And if the absolute value of b is greater than 1, it will shrink. All you need to know to do, though, is just divide by d. Okay. So to reiterate, do the opposite of c and then divide by b to your original x values. Here's an example of a horizontal shrink right here, sine of 3x. Alright, next we're going to do a, vertical stretch, shrink, flip. If a is less than 0, it will flip. If the absolute value of a is less than 1, it will shrink. If the absolute value of a is bigger than 1, it will stretch. All you need to know to do is take your original y values and multiply them by a. That will give you the vertical stretch, shrink, slash, flip. And finally, if d is positive, it will shift up. If d is negative, it will shift down. And you will add or subtract d to those y values that you just multiplied by a. To summarize the entire thing, and this is probably the easiest of everything we've done in this video. The proof is a little bit hard to understand. You're going to take your original x values, you're going to do the opposite of whatever c is. If c is positive, you subtract. If c is negative, you add. Or if it's minus c, you add. Then you're going to take those x values and divide them by b. Okay, once you do that, you'll have your final x values. Next, you're going to take your original y values and multiply them by a. And finally, you're going to take whatever that result is and either add d or subtract d, depending on if it's plus d or minus d. You're going to do the same as what it is. Again, it's more straightforward for your y transformations. When we put all that together, I tell my students that is called CBAD. Okay, it's called CBAD. Just remember, do the opposite of whatever x is. If it's plus c, you subtract. If it's minus c, you add. You're always going to divide by b, even though it's b times x. And then for your y values, you do exactly what you see in the equation. You multiply the parent y values by a, and then you add d if it's plus d, you subtract d if it's minus. That's it for this preliminary video of function transformations. If you have any other questions about it, let me know.